Okay, so in this video I'm going to run through the questions for quiz 14. This is a revision quiz on CC 13, 14 and 15, which are the three topics that we would have done at the start of this year before your mock. I'm not going to go through every question because a lot of these questions have featured either on previous videos or in previous quizzes. I'm just going to do the questions that I think you might struggle with most and those where the mark scheme maybe isn't quite as helpful. This question here came up on your mock. You might remember it. It's also on your carousel quiz, but a lot of you got it wrong on your mock. When you're drawing these activation energy diagrams, the activation energy has to start at the reactants and go to the top of the hill. A lot of you chose Q in your mock. You just went from the very bottom of the graph. It doesn't go from the bottom of the graph. Wherever the reactants start, the activation energy starts and it goes to the top of the hill. So the answer there is R. This question was quite well answered in your mocks. I think we got really good at these. You have to look at the number of bonds broken and then the number of bonds formed. So they've drawn out the molecules for you. You can see you need to break. If I just divide my reaction in two, so this is the reactant side, I need to break an N triple bond N. There's just one of them, so it's going to be 944. I've got a HH bond, 436, but there are 3 molecules of HH, so it's 3 times that HH bond. Then I'll add up those values and get my value for bond broken. Bond form, you see you're making an NH bond, but you are making 1, 2, 3 NH bonds, and this number 2 tells you that you've got 2 NH3s. So in other words, you would need to draw that molecule again, and then you'll see you've got 4, 5, 6 NH bonds in total. So that's why I'm timesing it by 6. So you work out this side, you work out this side, and then it's reactants minus products gives you your answer, and make sure to include your sign. The next one is a 6 marker. We can't just ignore 6 markers and always skip them because there's stuff in here that you can definitely answer. They're asking you about rates of reaction. They have given you some data. So they're showing you 3 different experiments. They've got the concentration and they're changing the concentration in one experiment. They've got temperature and they've changed the temperature. And then it's time for cross to become invisible. So if you remember the disappearing cross method, you put a conical flask on top of a cross, and because you form a solid, the cross becomes invisible. Now the quicker the cross becomes invisible, the quicker the reaction is taking place. So when I look at my results here, experiment 3, it only takes 20 seconds for that cross to become invisible. That means it only takes 20 seconds for the solid to form. That reaction is really fast. On the other hand, over here it's taking 320 seconds for the cross to become invisible. The reaction is much slower. So you need to, if we look at the question, explain in terms of behavior of particles how changing the temperature and changing the concentration affects the rate, okay? And you have to use these results. So what I've done, okay, is I've decided I'm going to talk about temperature first. You're asked to talk about temperature and concentration. I'm going to write a little paragraph on temperature. And when I want to talk about temperature using this data, what I want the temperature to change, but I want the concentration to stay the same. And that's why I'm looking only at experiment 1 and experiment 2. The concentration is the same. The only thing that's changing is the temperature. And when you change that temperature, you'll see that the cross disappears much faster. And that tells me that an increase in temperature increases the reaction. So I've written that I'm talking about temperature and I'm just looking at experiment 1 and experiment 2. And then I have to state some data from the table, and I said it takes 80 seconds for the cross to disappear at 40 degrees Celsius, but 320 at 20 degrees Celsius. I've then mentioned that concentration stays the same, but you can see that I'm talking about experiment 1 and experiment 2. So then I can say that because you've got an increased temperature and the cross disappears faster, I can say that this shows that rate increases as temperature increases. Now I do then have to explain that in terms of particles, which I didn't write out, but you would have to. So why does temperature cause an increase in the rate of reaction? You will say if you increase temperature, okay, so to finish this off, you would have to say an increase in temperature increases the kinetic energy. You can say the particles are moving faster, and if the particles are moving faster, you get an increase in the frequency of collisions. Don't say more collisions, say an increase in the frequency of collisions. You could also say that at higher temperatures, more particles have the necessary activation energy, So there will be more successful collisions. Now the next thing I need to talk about is concentration. So when I'm talking about concentration, I'm going to look at experiments 2 and 3. And the reason is because temperature stays exactly the same, it stays at 40, but concentration increases. And when I increase that concentration, I can see the cross disappears much faster than when I was using a lower concentration. So I just say that, okay? I say I'm talking about concentration, I'm comparing experiment 2 and 3. And then I just, from the table, it takes 20 seconds for cross to disappear at 40 grams per decimeters cubed. And I can read that from my table as well. I know what the unit is from the table. 40 grams per decimeters cubed is concentration, but it takes 80 seconds at 10 grams per decimeters cubed. The temperature has stayed the same. This means I can say that if you increase the concentration, you do increase the rate. And again, I have to explain why. So if you increase concentration, what you're actually doing is you're increasing the number of particles. You're just putting more particles in there. And if you've got more particles in there, you are going to increase the frequency of collisions. Now, if you're writing the answer, you can't just use an arrow to show increase. I'm just using shorthand here. But that would be a full 6 marks easy. Okay, you wouldn't even need to write all of that to get 6 marks. You just need to make sure you're referring back to the table. You're talking about temperature, and you're talking about concentration, and you're telling me something in terms of particles. You should have the word frequency of collisions in your answer someplace. The next question also came up in your mock, and to be fair, there should be a graph that goes with this question, which this is making it slightly harder. But if you see here, what's essentially happening is the rate of reaction is halving. So half of 52 is 26, half of 26 is 13, half of 13 is not exactly 6. But as I said, there should have been a graph to help you work this out. I think in the exam, most of us were getting this right. And then it says, state and explain what happens to the rate of reaction as the acid reacts with the marble chips. Now we can see here these numbers represent rate of reaction: 52, 26, 13, 6 and 3. So over time the rate of reaction is slowing down. So your first thing will be the rate of reaction slows down, and then you need to say why, because the particles are all getting used up, and then you're going to have less frequent collisions. Most of this I think you'll get from the mark scheme. This one here is about calculating the rate using a tangent. So in this particular question, they've drawn the tangent for you. They don't have to do that. Remember, if you're drawing a tangent, wherever they ask you about the rate, so in this case, they've drawn the tangent there at around, was it 25? Yeah, around there, 25. So the tangent is a line that cuts the graph in one point and one point only. And once you've got the tangent drawn, you have to get the slope or the gradient of that tangent. So what I've done is I've written the coordinates of 2 points. So I've taken this point here right at the top of the line, and I've said this point has a value of 60 on the x-axis, and I've said it's got a value of 44. So you're going up in twos, you're going 40, 42, 44. I've said it got a value of 44 on the y. And then I've taken this point here that's cutting the y-axis, and I said it's got a value of 0 on the x-axis, and I said because it's in between those two lines, I said it was 15 on the y. So it's going 10, 12, 14, 16. It's not quite at 16, so I've said the value is 15. And once I've got my points picked, it's changing y. So the difference between y points is 44 and 15 is 29, over change in x, 60 and 0, the difference is 60. I divide and I get 0.48. And on the mark scheme, it gives it a range. As long as your answer is between 0.44 and 0.52, you've got the right answer. So you could choose slightly different points, or you could read this slightly differently, and you could say that this was 0.16, and you'll still be within range and you'll still get your marks. Next question I wanted to go through, again another 6 marker. You can't just ignore them because they're 6 markers. Okay, there's stuff that you can say here. So it says it's drawn this reaction, and it says discuss what catalysts do and their effect on the activation energy, and you can use figure 8 to illustrate your answers. Effectively, it's a 6 marker that says just tell me all you know about catalysts. Okay, and you come across them in biology as well, so you should have something to say here. So I've written catalysts speed up the rate of reaction without getting used up. Okay, so it's something you can add them to a reaction, they make it faster, but they themselves don't change. So there's your first sentence. How do they do this? They provide an alternative route with lower activation energy. So if you remember, activation energy is the minimum amount of energy that particles need to react. So let's say both of these particles had 100 kilojoules of energy, and they need to collide, and they need to collide with force. What if 100 kilojoules of energy isn't enough force? Okay, they collide, but then they just bounce back off each other. they don't actually react. I would say that these particles do not have the activation energy. But what a catalyst does, it doesn't give the particles more energy. It basically just lowers the standard. And before the catalyst, 100 kilojoules of energy was not enough. And now you add the catalyst and 100 kilojoules of energy is enough. It's like if I lower the pass mark in a test. Okay, first of all, I say you need to have 70% for a 9. Then I change my mind and say actually 65 will do, more of you will get a 9. That's what catalysts do. They lower the activation energy, they're kind of lowering the pass mark. And the way they do this is they provide an alternative route. So in your booklet you'll see a picture where you have 2 routes, cars going over a mountain and then cars going through a tunnel to get to the other side of the mountain. It obviously takes less energy to go through the tunnel than to go over the mountain, and that's what catalysts can do. They provide a different route for the energy for the reaction to take place, and the other route they provide requires less energy. So provide an alternative route. The way you phrase it is this: provide an alternative route with lower activation energy, and that means you're going to have more frequent successful collisions. And they ask you to illustrate your answer on this. So we know that this here is the activation energy from the reactants to the top of the hill. That's your activation energy. And that's the activation energy without a catalyst. All right. This lowers the activation energy. So what I will be drawing is this. I just don't go as high with the hill. And now this is the activation energy after I add a catalyst. It has just lowered that activation energy. Now much more particles will have the energy they need to react. Okay. Last thing I've said here, they have asked for some examples of catalysts. Now you can say enzymes, which you learn about in biology. They'll give you the mark for that. I've spoken about something else. We've come across it recently in fuel, catalytic converters. You find them in engines and they take harmful nitrogen oxides, turn them back into nitrogen and oxygen. Cracking reactions as well that we've looked at recently, and they require catalysts, and there'll be another reaction that we're going to be studying after half term, the Haber process, which will also require a catalyst. So you should have quite a few examples of catalysts when you're going into your exam, but this will be more than enough to get you your 6 marks. So only one other question, because lots of these we've seen before, and you'll find the answers in the marks here. There's just one other one I'm going to do, this one here about being reduced. Just to remind you, usually when we do these, we write the ionic equation first. It makes it a little bit easier. So I'll remind you, sodium iodide is ionic. It's got a metal and a non-metal. Bromine is covalent, 2 non-metals. Sodium iodide, ionic, metal, non-metal. Iodine, covalent, 2 non-metals. And if it's ionic, I can split it up into ions. Sodium's in group 1 with a +1 charge. Iodine's in group 7 with a -1 charge. Bromine's covalent, it doesn't change. Sodium bromide, sodium's in group 1, a +1 charge. Bromine's in group 7, a -1 charge. Iodine's covalent, it doesn't change. And you'll see that the sodiums cancel out. And now that I've got my charges, I'll be able to see what's being oxidized and what's being reduced. And we know oil rig, reduction is gain of electrons. So what's gaining electrons? All right, so the first thing I'm going to look at is how iodine changes. So iodine has a negative charge on the left. It has no charge on the right. A negative charge means it had gained an electron. So on the left hand side it has an extra electron, but on the right hand side it doesn't have that electron anymore. I know that because it doesn't have a charge anymore. So iodine must be losing electrons. Okay, it had a negative charge, it lost that electron, now it's not charged anymore. So iodide, that I minus ion, is being oxidized. That means bromine must be being reduced. So if I write down bromine, I've got Br2 and it's going to 2Br minus. So I just write everything down exactly the same. Br2 to Br minus. Br2 is on the left of my arrow, Br minus is on the right. And if I wanted to have a negative charge, I know it has to gain electrons. Because there are 2 bromines, it needs to gain 2 electrons. So explain which substance is being reduced. This is an explanation, okay? But you can say this is reduction, and you can say that bromine has gained electrons, and gaining electrons is reduction. Okay, but this half equation, if you can write it, it will get you all of your marks. If you've got any other questions about ones I haven't gone through, please do ask me, but I think a lot of the others we have seen before, and you will find the answers on your mark scheme.